Hey, good Sunday morning, YouTubes. This one's a little story about just one, a few days in a career, eh? So, I worked as a field service engineer, installing, servicing, adding channels to, or repairing optical emission spectrometers. Uh, so, these are lab instruments that do elemental analysis. So, they look for elements from the periodic table and more. That's what they're built for. Now, these machines are $250,000 machines. This is 1980s. They've been replaced. There is a whole new generation of these machines out now that the new ones look nothing like the old ones. So anyway, I get a service call, trip set up, fly over to Baton Rouge Airport in Louisiana, get my rental car, and I drive. And I'm thinking, okay, any place I've seen this instrument before was a very clean lab or an industrial environment that might not be so clean. So an industrial, they're testing for metals in steel, so they've only got 5 channels. It's still a $250,000 instrument, but it's getting used a little different. Maybe cheaper. They might have had something a little bit cheaper, but the inductively coupled argon plasma ones that I installed were very expensive. So I'm going to this site to replace capacitors. They've already been ordered because we knew that they had failed because they leak oil. Now these capacitors are the size of a car muffler. So they're part of what's called a pulse forming network that makes a super high voltage pulse charge that fires the argon plasma generator, or the energy generator to make an argon plasma. This is a high frequency signal in an antenna, and this little pulse, this big pulse forming network, sets up a charge to fire some type of emitter tube, and that ionizes the energy around argon, and that's how you sample, using argon plasma sampling. So anyway, I've got these capacitors, which are, they're thousands of dollars each anyway. They've been shipped there waiting for me. And I'm going to rebuild a pulse forming network. Go Google that one if you're interested. It's what makes radar systems work as well. So I get to the site, I get to the building, and it's off in the middle of the bayou. This is a cross between the swamp thing and advanced sciences. Just the look of the place. It's a ramshackle swamp building. So I get inside, and the challenge is now this pulse forming network requires 3-phase power, because the way it builds that high energy pulse, megawatts of power in that tiny little pulse, is by adding up the sine waves from 3-phase power. So that building didn't have 3-phase. None of his other instruments needed it, and the cost of running it out to the bayou was somewhere at, tens of thousands of dollars. So he bought a 2-phase to 3-phase AC converter. So that's an industrial thing that usually runs motors. It runs inductive loads 99% of the time. And it's engineered for industrial loads, big motors. Well, this pulse forming network had a step-up transformer before it. So it was a different type of coupling between the inductive load and charging a capacitive load for the pulse forming network. So the feed into the network, the feed into the network was slightly out of phase from the two-phase to three-phase conversion, and was causing an imbalance in the capacitive network and charge circuit that was making the capacitors overheat. So besides replacing the capacitors, wearing rubber gloves, because there's a good chance that there were PCBs in the oils, just the age of the capacitors and the time. So science and science applied engineering coming together to try to make something work that didn't. Those capacitors shouldn't have gone out, but they do age. They will age with heat, and the heat buildup is because of a very minor fluctuation in three-phase power. So I'm sure, people are familiar with this type of challenge and problem when you're doing high, pulse forming network type of work. So ended up resolving that, hopefully. Never did get feedback, but I know for a few years it worked anyway. So inside this shed is this very expensive inductively coupled argon plasma optical emission spectrometer. Next to it is a scanning electron microscope. And this is in a tin building. It was fairly climate controlled, but just interesting stuff. So what did he do? Why all this equipment? Well, he made a living off of inspecting failed materials, mostly for the shipping industry. This is bayous, Louisiana, right? Or the oil industry. So when something cracks or something fails, the materials get sent off for evaluation as to why they did it. Failure mode engineering analysis. And that's what this shop did. He would take steel and put it under the scanning electron microscope. He would sample for constituents in materials to see if they had been wrong ratios for metallurgy. Ceramics were a big one, testing the contents of the ceramic or titanium rotors on a jet. That was one of the applications for these instruments. Testing the biological uptake of toxins in plants from Louisiana bayous. That was an application. Testing the groundwater of North America to find aquifer flows and some contamination information requested by the federal government was an application at Exxon. Looking for minerals to be extracted from water down in large plants in Texas. That was an application. We used to, and we probably still do, remove magnesium or titanium or other metals from water itself. It was a World War II initiative initially to get those precious metals for the wartime. This is what we do with these sciences, with these instruments. When a chemical engineer, when a chemist applies his knowledge, he uses these tools to find very discrete information about our lives. That's what the instrument did. So, like I said, this was, if you could imagine a red-green show, having one of these instruments, that's kind of what it was like, only there was more in the lab. He would take and digest metals to be able to do a liquid sample of the metals. So there's complex techniques and processes and standards to doing the procedures to get the measurements correct that all of these labs had unique to them. A lot of them are called ISO standards. They come out of international standards organizations, best practices, common practices, and the education from the sciences. So that's 1,000-mile view of a day in the Louisiana bayous. Blue State.